Hello everybody, I hope you can hear my voice well now. Today I am going to explain you about a topic called Einstein's coefficients in the light matter uh, interactions. Einstein's A and B coefficients especially. Einstein has considered the rate equations for spontaneous emission, stimulated emission, and also absorption of radiation in the case of the interaction of light photons with two level atoms. So let me draw one two level atom like this with the lower level as number 1 and the upper level as number 2, and let me call their energies as E1 for lower and E2 for upper level. Then so let us consider some collection of these kind of two level atoms, and let us say the total number of those atoms as n, and let us say that they're occupying some space with volume v. So out of these n atoms, some atoms could be having electron in them in the lower level. So if you count such kind of atoms and if you get their number as n1, this is what we actually call as population of the first level, population of level number 1. And out of these n atoms, if you count atoms with the electron sitting in the upper energy level, and if you get the number as n2, so you call that as the population of level number 2. Actually this population is defined as a number per unit volume, so you should divide this thing by the volume of that entire space of the atoms. So this is in a way is called number density of the atoms with electron sitting in level number 1 and the electron sitting in level number 2. So they are also called as populations of level number 1 and level number 2. So after actually seeing these populations, we can actually kind of write the rate equations because of three processes. The first process we consider is actually for spontaneous emission of radiation. So for that, the number density of the upper level will actually kind of decrease because the electron which is sitting in the upper level will come down to lower level because of spontaneous emission process. So the rate equation for that can be written as dN2 by dt as negative A and N2. So this A is actually called as Einstein's A coefficient, and so this is actually because of spontaneous emission. So let me put SP and E as abbreviation for this process. And because of absorption, the because of absorption also we may have increase of this one, but that we consider a bit later. But now we consider stimulated emission of radiation. So because of that also we can have change of N2, and it's also decay process for N2. That's why we take a negative sign here. And Einstein has written using some coefficients called beta-1 coefficient, and of course there was some rho spectral energy density of black body, because he considered that all collection of atoms are actually in thermal equilibrium with a black body. That's why we are writing rho here, spectral energy density of a black body. and then this is multiplied to the number density of level number 2 n2. So this process, I mean this rate equation is because of stimulated emission process. And so if you write the rate of rate equation for the upper level, when we take into account these two processes, then we can write a master equation for dn2 by dt, which is summation of these two terms minus a n2 and b21 rho and n2. And when we consider the third process, which is absorption of radiation, and in that process the population of lower level will decrease, and so for that we can write the rate equation as dn1 by dt is equals to minus, again another B coefficient of Einstein, which is B12 now, and the spectral energy density of black body rho, and the number density of the lower level n1. So this is actually we can call as equation number 1 and equation number 2. So at thermal equilibrium, what we can expect is the rate of change of n2 should be equal to the rate of change of n1. So that's why we can actually equate the right hand sides of equation number 1 and 2. So if you do so, let me erase here for space. So if you do so, what can we do is we can write this minus a n2 minus b to 1 rho into n2 being equal to minus b12 rho and n1. So what we can do is we can actually send this first term to the right hand side and bring this right hand side term toward the left side, and we can also take the common factor rho out. So if you do so, we get b12 n1 minus b21 n2 whole thing being equal to a n2. So this is what we get, and from this what we can do is we can actually let me erase this stuff here, and we can actually kind of write this expression for rho. If you write expression for rho, we can actually have a n2 whole thing divided by b12 n1 minus b21 n2, and we can actually in the denominator take n2 as common factor out. So if you do so, numerator can be written as it is, and n2 can go here, and here we write b12, this is n1 here, so n1 divided by n2 minus b21 here. So we can actually cancel out n2 and n2 here. Perhaps I should have even taken this b21 also outside. So if you do so, we get a divided by b21 into b12 divided by b21 into n1 by n2 minus 1. So this is what we get for rho, the spectral energy density of a black body. And remember, this sample is actually kind of in thermal equilibrium. That's where we were able to actually equate dn1 by dt is equals to dn2 by dt. So at thermal equilibrium, there is actually something called Boltzmann statistics, which the energy levels should satisfy, and because of that, this n1 by n2 can be written in a exponential, in terms of some exponentials. So let me actually write that thing straight away, I think. So this n1 by n2 can be written as exponential e2 minus e1 divided by kt. So we can write this thing in this form because of the Boltzmann statistics. And if you actually take E2 minus E1 as the h nu, the energy of the photon which is interacting with the two levels, then we can even write this n1 by n2 as the exponential h nu divided by kt. So if you use this fact in this expression for rho, then we can write the rho as the spectral energy density, rho as A divided by B21 and whole thing divided by B12 divided by B21 into exponential h nu by kt minus 1. So this is what we can write. But remember, this spectral energy density expression should be actually kind of same as that derived by Mr. Max Planck for explanation of the spectrum of black body radiation. So this should be, as per Mr. Max Planck, equals to 8 pi nu square by c cube into h nu divided by exponential h nu by kt minus 1. This is actually from the topic of black body radiation. So if you call this as the number I and this as number double I mean Roman 2, then this and this should be actually kind of equal. So because of that fact, we can actually say that numerator A by B21 wait a second, here the bracket is not just for this one but including all this thing. This is what we get. And so if you compare this equation number Roman 1 and Roman 2, then we can actually write A divided by B21 being equals to 8 pi nu square into h nu by c cube, and B12 by B21 should be equal to 1. B12 by B21 being equals to 1. So we can call this as equation number 3, I think, and this one as number 4. So these equations number 3 and 4, which relate the Einstein's A coefficients and B coefficients, are called the relationships among Einstein's coefficients. So we can say that the B12 is equals to B21 and A is equals to B21 into this factor. That's it in this video, and I will meet you with some other video next time. Thank you. Bye bye.